Conduction in relation to band diagrams. This is Piyush Mirani and I am going to explain you the phenomenon of conduction with the help of E versus K diagram. So here we have a E versus K diagram that we see in a reduced zone scheme, and suppose the first two bands are completely filled with electrons and the third and the fourth bands are completely empty. So at 0 Kelvin, as the third and the fourth bands do not have any electron for conduction, therefore they won't contribute to the current. Whereas the first and second band are completely filled. So if we apply the electric field, the k states of the electrons will change with time. But as there are no available k states for electron can go into, so only the k states of electrons will interchange. So the overall difference, the overall picture of the first and second band will not change. Therefore, the first and second band will not contribute to the current. So if you go to the room temperature, at room temperature, few electrons will jump to the higher excited band, which will result in partially filled second and third bands. Here I have shown the empty states in second band by yellow dots. So here, as these two bands are partially filled, second and third, these will contribute to the current, whereas the first and the fourth band will not contribute because the first band is completely filled and the fourth band is completely empty. So now let's discuss the contribution to the current by third and second band. So if we apply electric field, the electron will start to drift. So the equation of current is given by the equation of current by the third band is given by I3 is equal to minus q by L summation of velocities over all the field states. So here in our example we have three electrons, so we will do the summation of velocities over three electrons. So, and in second band, similarly, I2 is equal to minus q by L summation of velocities over all the filled state. But the problem arises that for a particular material, we can have n number of primitive unit cell. Therefore, we will have n number of k states in the first Brillouin zone. Since number of primitive cells in a material could be of order of Avogadro number, therefore we will have Avogadro number of states, and this makes the summation over Avogadro number are quite difficult. So what we can do is, here, here we define imaginary positive charge particles as holes so that we can write the equation as summation of velocities over all the states. This is for a particular band. So summation of velocities over all the states is equal to summation over filled states plus summation over empty states of velocities will be equal to 0. Uh, the reason we need to introduce holes because summation over all the empty states we cannot calculate because these are empty states. The empty states do not have electrons, so we cannot calculate velocities for that. So we need to introduce a hole like imaginary particles so that we can calculate this term and we can write this equation as this. So therefore we can then write the equation of current I2 as which was minus q by L summation over all velocities of filled state. We can write that as plus q by L summation over all the empty states of velocities. What this does is that before we were going to do the summation over Avogadro number, but here we are just going to do the summation over only the empty states, which makes the calculation a lot easier. Therefore, this was the contribution by the second band. So we conclude that the completely empty bands do not contribute to the current, completely filled bands do not contribute to the current, nearly empty bands do contribute to the current, which is due to electrons, almost filled bands do also contribute to the current, which is due to hole-like particles, and the most important, in a particular band, electrons or holes can contribute to the current, but not both. And that's all for this video. Thank you.